Hi, my name is Yunxuan Lian from National Yangming Jiaotong University. I'll present our work, Parametric Dimension Reduction by Preserving Local Structure. Dimension reduction techniques are widely utilized to facilitate data exploration and visual analysis. The goal is to project high-dimensional data to low-dimensional embedding, while retaining either global or local data structures. The most famous dimension reduction method is t-SNE. It attempts to maximize the probability of nearby or distinct points in high-dimensional space being nearby or distinct in low-dimensional space. t-SNE models the similarity of high-dimensional data points xi and xj by the joint probability pij and employs a heavy-tail student t distribution to compute a weight wij for computing the low-dimensional data point distribution. Let P and Q be the joint distributions of Pij and Qij respectively. And t-SNE minimizes the K divergence of the joint distribution. t-SNE is a non-parametric dimension reduction method. The advantage of non-parametric method is high flexibility when determining the position of data points in a low-dimensional space. However, non-parametric methods lack generalization, which cannot apply the transformation obtained from the given dataset to reduce the dimensionality of new data points. Therefore, our goal is to extend t-SNE from non-parametric to parametric by training neural networks. The advantage of this parametric extension is that it can reduce the dimensionality of unseen data, which is beneficial for streamlining data visualization. Previous methods claimed that neural networks would get stuck in poor local minima if the networks are trained by directly optimizing the t-SNE objective function. Therefore, they either require a network pre-training step by the restricted Boltzmann machine or intermediate results obtained from the traditional non-parametric t-SNE when learning the transformation. However, we found the recent training technique can effectively prevent the training problem, particularly the add-on optimizer and liquid ReLU activation function. This figure shows the results achieved by the different optimizers and activation functions. Specifically, ReLU and liquid ReLU can avoid the gradient vanish problem that commonly appears in the sigmoid function. And the add-on optimizer considers the momentum to prevent high oscillation when partial samples are utilized to update network parameters. Hence, we point out that the proper activation function and optimizer are essential when training neural networks to reduce the data dimensionality. In addition to generalization, the computation complexity of traditional t-SNE is expensive because it has to determine the joint distribution of each pair of data points whenever the projected low-dimensional data are updated. Specifically, the complexity is big O n squared, where n is the number of data points. Fortunately, the independent and identically distributed assumption enables neural networks to be trained using the stochastic gradient descent method, where in each iteration, only a small amount of data are used to update network parameters. Let B be the batch size. The complexity is then reduced from the big O n squared to big O b squared in each iteration. Here we show the evaluation results. All evaluation focus on generalization. The projection parameters were optimized on the training set and then evaluated on the testing set. This slide shows the 2D embedding projected by the baselines and our method. In an embedding, each dot is a sample, and each distinct color indicates a class. Therefore, dots in the same color should gather, and dots in different colors should separate. As can be seen, our method generated good 2D embeddings because of noticeable boundaries between clusters. Besides the visual comparison, we quantitatively evaluated the dimension reduction results. Since dimension reduction is an ill-posed problem, several metrics should be jointly used for evaluation. We consider three well-known and easily interpretable metrics. They are trustworthiness, continuity, and neighborhood hit. The upper part of this table shows the results generated by the baselines and our methods, in which the best parameters were chosen for each dataset. To evaluate whether the methods were robust to the given parameters, we also selected a parameter for each method that can be worked best on all datasets, and the results are shown at the bottom of this table. As can be seen, our method outperformed baselines in most of the datasets. Finally, we compare the computation time of our method and baselines on selected datasets. Our method is only slower than a linear method PCA because our network is training using a stochastic gradient descent method. We refer audience to our paper for the details of the evaluation results. Thank you for your attention. Our source code is publicly available.